Did it go? There it goes. All right. So heaps. Remember that heaps are a very special kind of binary tree where every node satisfies the heap property. If it's a max heap, you're going to store the maximum thing at the top because every parent's going to be bigger than or equal to its children. That's going to force the maximum to bubble up or percolate up to the top if you keep all that stuff in check. It's a complete binary tree in that every row column is filled in. Every piece of that tree is like perfect up until maybe the last row. And then it's filled in from left to right. And you might think that's really hard to keep track of, but no, not if we keep track of it with a vector. So we store the tree as a vector, and that lets us move around with indices. Index 0 is the root. And if you want to go left, do that. If you want to go right, do that. If you want to find the parent of u, you're always at an index, not a pointer to yourself anymore. You calculate it that way, and then you can move around. You just have to remember, like, stop when you get to a leaf. Make sure you can go left. Make sure that index exists, right? That's kind of how that's your dereferencing null check. Go and see if you can do it. Am I already 0? If so, there is no parent above me. There's some if statements involved because it's just indices, but at the end of the day, it's essentially you're moving around a tree with pointers, but they're really indices. All right, so we're talking about at the end, it's like, all right, we have this heap. It's good at keeping track of the maximum thing or the minimum thing if it's a min heap. And here's kind of what I want to be able to do to it. We've come up with a priority queue abstract data type. Let's define the operations that I would want to do on something that I could implement with a heap. So yeah, you want to be able to push it. Like, think of it as a queue where you're pushing things to it, like you're putting values in still, but when you pop or look at things, what you get to see is the maximum thing or the minimum thing if it's a min heap. So pop gets rid of, it's always the root. Peek shows you always the root. So that's kind of what you want to be able to do, and that's always constant time for those at least. Is empty, checks if the heap is empty, like you want to keep on popping as long as it's not empty. Usually that's something that we did for normal queues, right, in our lab. Get the length, see how big it is, how many things are in it if you need that fact. So yeah, that was cool. We also talked about Git and GitHub, consider that. But let's keep on trucking because it's not too hard. All right. So if you want to push to your priority queue, it's just like you're gonna do the insertion operation on your underlying heap. So what you're gonna say is like somebody's got right a priority queue, call it like PQ or something. You've made your priority queue object, and secretly inside of that, your member variable, if you're using a heap to keep track of it, it's just like, here's my heap. It's a vector. Boop, just like that. And if you say pq.push, like 42, your job is to do the insertion on heap. Just like, what is that? You push back the 42 to the vector, right? And then you know that this is equivalent to some tree that looks something like this. I don't know. Like maybe this was the new thing. There it is right there. You have to like potentially bubble it up to the top. That's all. So like this maybe gets to like be moved around a little bit, swapping things around, and maybe eventually it'll hit up there, up the tree. Okay? So yeah, push is just insert. It's just like all of these operations have a corresponding heap operation. Excuse me, thank you. So yeah, that's how that one works. And then pop, you can imagine, it's the remove. It's the remove from the root of your tree, which is the thing at index 0 in your heap data structure. Okay? So yeah, just like remove the node at index 0, like you've got a priority queue object now, and secretly, deep down, you're storing it using a heap. And all it means to get rid of the root is you move it down, you swap it with the very last node in the tree, which is always going to be your last index, and your root's always going to be index 0. So you're always going to do that exact swap. Swap the first thing with the last thing. And then you can pop back that thing. And then most likely the thing that you put up here, it was like one of the smallest things in the tree, in the heap. And so it doesn't belong up there really. It needs to be bubbled down. It's like, woo, get it to there or something. So there you go. It's remove the root. So not too bad, but that's what it's going to look like, right? Deep down, because we know the data structure involved. But as far as the user is concerned, they're saying pop, and they just like expect the maximum thing or the minimum thing to be gone now. Okay. So that's how that's going to work. That's pop. Shout out if you have any questions about this, but we're essentially just turning every heap operation into something with one of these names, but we already know what the operations are. So you got those. Peak. We can see why it's constant time. You go and look at the root of your heap that you're storing this priority queue using, and so that's just going to give you back the max or the min, right? If it was a min heap. What is the min but the maximal smallest thing? So you got your priority queue. What does that mean when you say, like, I can give you the code, in fact, if you call your heap H. What does it mean to peak? Just like, go right here, return that value. Return H at 0. Like, that's the implementation of peak, isn't it? Can't do anything other than that. Yeah, so that's peak. Is empty and size are just as simple as you would think they are because you have a vector, right? If you have a vector that is your heap, here's your priority queue. Whee. You got a vector that is your heap. Call it H. Just like go look at it. Like, hello. How many things are in this vector? Is the vector empty? The vector has an empty root actually, doesn't it? It's like, go ask the vector. See if it's empty. Same for size. It's like, hey, we got a heap H. We have a vector called H that represents our heap. Just like, go give back how many elements the vector knows. The vector knows its size. Yeah. So that's honestly it. Does that make enough sense? Like, if you want to implement a priority queue ADT, it is in your best interest to use a heap, and to implement all of these operations is just do the corresponding heap operation. That's all it is. Push is insert, pop is remove the root, peak is go get the thing at the root, is empty in size, or look at the size of the underlying vector. See if it's empty, see how big it is. Okay? Any questions about that? So yeah, it's a little philosophical. Like, we've given them new names, we're defining it in terms of operations. It's still the bet. You could implement all of these things without using heaps, right? If you really wanted to. Just like use a normal vector, go through it, do what you gotta do. But you get the best speed, best bang for your buck if you use a heap. So yeah, that's most of it. And you know that you have a priority queue already implemented for you by the C++ people. So let's go look at it and see what happens. Because usually when you have something given to you by the library, like it's been battle tested. Like, we're learning to make our own in this class so that we can learn like how to use somebody else's library one day. Like, you're not going to go make your own heap most likely when you go into industry. You're going to use somebody else's. But at least now you know the trade-offs and like what's going on under the hood. That's what we care about. So the priority queue type lives in the queue header. It has the normal queue as well as this one. So let's go look at it. Let's go take a look at the documentation, and we will go from there. Dun, dun, dun. So let's see. We got it's in the queue type, and you have a normal queue, which is a FIFO queue, first in, first out queue. And we got priority queue, which is queue with priority in priority order. Okay, this is gonna get a little tricky because it's templated. Like, it's gonna work. It's gonna work for normal values that are already in C++, like doubles and ints. Like, if you make a priority queue of ints, it's gonna work the way you expect. But if you make your own type, then you have to tell it, like, what does it mean to be the max or the min? So that's what all these other template things are. You can give 3 things if you want to the priority queue. First, the thing is the type. The type involved what things are we placing into the priority queue, just like every other container type uses that T, right? And then you tell it, how do you want to store the values? Something that can have indices. So like they're saying, by default, it's a vector. They are using a vector as their heap. And then also, you can tell it how to compare the values of that type T. You can define your own meaning, give meaning to maximum in different ways. All right? That's the idea. So yeah, if you read it, like it eventually makes it. Priority queues are a type of container adapters specifically designed such that its first element is always the greatest of the elements it contains according to some strict weak ordering criterion, which is a bunch of math that I will try to talk about a little bit, at least. Okay? So yeah, it's I highly encourage you to read all the rest. But what do we get? We get empty, we get size, it's called top, which is some weird combination of stack ideas and queue ideas. Like it's the top of the priority queue, they're calling it. That's the thing at the highest place, I guess, the maximum, which I guess metaphorically makes sense. Push is insertion. In place is something similar to insertion. Pop is remove with, I think it's void. It doesn't give the thing back. It doesn't give back a copy. So if you want it, you better use top first to get the thing. It'll give you back it as a reference if you want to just change it. Otherwise, you can copy it in if you need to. So yeah, top just always shows you what's at the front of your priority queue, essentially. Yeah, all of the other ones are as you would expect. So yeah, let's have some words about all that. So okay, priority queue, you make one. It's got 3 template parameters. The first was the T type, the thing that you're putting into your priority queue. The second thing is like, what are you using to represent the heap? It's something that needs to be randomly accessed. So it could be a vector. It could also have been an array. If you want to, there's an array type called array in C++. It's a little weird, but it's possible to do that one or something else. You can make your own vector type, put it in there. That's okay. The third thing is a comparison class. Right? A class that tells you how to compare, or even a function maybe, how to compare 2 t-values. 2 t-values, and it's going to default to the less than operation, even though it's making a maximum heap. So that's weird in itself. We'll get there. All right. So what it's going to do is it's going to use less by default, and so that the way it uses it is greater than. It's going to like use it backwards. I'll show that to you. All right. So it defaults to less of t, which is a built-into C++ comparison class that has an operator parenthesis overloaded. So it's like a function call on an object that you can do. That's what it means to be a comparison class. We'll get there again in just a second. Don't worry. It takes 2 things, and it returns the result of A less than B. All right? So that's what it does by default, and that's going to work for any type as long as you've implemented operator less than. So as long as that exists for your custom type that you're using inside of your priority queue, you are set. You don't have to do anything else. You can leave the second and third things as the defaults. You're fine. Yeah, so it's by default a max heap, even though it's using less than. So what it's doing every time you push stuff, it's like, it's comparing like A less than B, and it's interpreting it backwards. It's using it, even though it's a less than operation, it's using it like a greater than operation. So it's calling it with 2 things, A and B, and it's trying to see, hey, should I put B before A? All right, so read this as, like it's trying to determine if this is true, it's saying that B has higher priority. This is from the perspective of the second thing that's being passed. All right? This will make more sense with examples. So it's saying that if this is true, B has higher priority. That's how it's defining it. Priority. If this is true. So it's like you just push something. It's going to call it kind of backwards, the less than operation. It's going to be asking, hey, should B come before A? If so, do this operation. Do this less than operation. So it's really using it like greater than. All right? It's doing it backwards. And that means then that you could turn a max heap into a min heap by changing the comparison from less than to greater than, because it's always from the perspective of the second thing. Like, if this is true, A greater than B at this point, it's saying that, all right, this one, the B should be prioritized if this is true. If you pass along that operator, that's going to prioritize smaller B's. Does that make sense? It's a little weird. It's a little weird. And so what's the best way to do this? Let's just have a normal example of heap stuff. It's and then we'll get into the idea of doing it in a different way. I think that would be the right idea. So yeah, at least at the start, let's just do it the normal way. Here's my example. Actually, asymptotically, it's okay, and it works out. A very good reason to want to use a priority queue, which is really a heap, is to sort things. is to sort things, and we can talk about the complexity of that because it's quite nice. All right. So here, if you are given a bunch of elements, you can shove them all into a priority queue, and if you want to use the defaults, you'll get all the values back when you pop them, right, in sorted order, reverse sorted order, biggest to small, still sorted technically. So that's kind of cool. So you can kind of do a process of sorting by, all right, you get a bunch of values. Let's say we've got, I don't know, 5 values, 1, 8, negative 42. So this is an array or a vector. There, the algorithm for doing this, like using a heap to sort them, is called heap sort, which is a nice natural sounding name for this process, called heap sort. And it should be able to turn, at least if we use the default stuff, this array or vector. We've got to put everything into a heap first, then we can replace all the elements as we pop them. But first we'll get the 8, right? If we pop it, then 7, then 1, then 0, then negative 42. So that's heap sort in action, right? It's like put it all into a priority queue, keep popping it and like pushing it onto a new vector, or you can replace the old one or something. I'll have you think about the running time complexity of this, though. All right. So go back and remember, all right, all the operations on heap stuff's running times. So we're going to need that in a second. Okay. Yeah, so let's do that. So we've got, let's call it just priority queue. Okay, so I would like to sort some stuff using queues. So the priority queue, it lives in the queue header. If I want to put everything that I've sorted, like I want to take a vector, give back a vector, like I need vector, of course, still. So let's just say like we've got these numbers, we want to sort them. We want to heap sort them. So I'll make a priority queue of ints, and so by default it's going to use a vector to store the heap, and it's going to compare them using the greater than, or sorry, the less than operation, but it prioritizes the second thing in that operation. So it's really turning it into a greater than operation. All right, so there's my priority queue, call it PQ, and I can push all these values in that order. 1, 1, 8, negative 42. We've got 1, 8, negative 42, 7, and 0. Okay, we got all those things. And so like that's the first step of a, like if you had a vector originally or something, you just like iterate through it, push all the values in order. And then you want to give back a vector of all the things as they were sorted. So sorted vec. And so we want to go through essentially this priority queue, pop it every time, get the value at the, it's called the top in this library. And just keep on putting it into that sorted vector, right? So remember that when I pop from PQ, I get things in priority order. And so the default's going to be biggest thing first. It's a max heap. So just forever, while the priority queue's empty operation is not true, empty gives back false. So while it's not true that the priority queue is empty, I have something to pop and look at. I still got a value up in there. So, all right, keep popping. That's what I want to do. I want to keep popping and adding to the sorted vector. And what does that entail? It's like, all right, the value that's at the top of the priority queue right now, I can get with pq.top or at the front, however you want to think about it. The highest priority thing is right there. It's that value. And that's the next thing to go into this vector. So push that. Sorted vec.push that new value. Okay, there it goes. And yeah, at that point, the value is still at the top. We got to get rid of it now with a pop. So pop that priority queue so that now I can look at the next thing underneath it. Yeah, do the next smallest thing. So that's the process. And I think that's what I wanted to say. Oh, sorry, it's push back to a vector. It's just push to a priority queue. Of course, it's push back to a vector. And then once we've got that, we got the sorted vec, we can go through it in order. For every integer called x in sorted vec, go and show it to me on the same line. And we'll break that line at the end. So that's the process. You push it all, you just keep on popping. And there we have it. Those are all the elements that we put in order, reverse order, into the vector. And so that does sorting for us. Makes sense, right? It's a good reason to want to use a heap. It's called heap sort if you need that ever. So any questions about this algorithm? Just like using the stuff that we get for free with heaps. Quite nice. So yeah, if we are happy with that, here is heap sort is kind of the whole idea of pushing and then do this loop. So I guess my question for you now is, with that in mind, oh wait, let's also do all this. There's the algorithm. I have a question for you now. So please get together with your neighbors. Remember the heap operation and I guess also vector operation running times. And let's see if you guys can write down and come up with and agree on the running time for heap sort. So here, let me go to the nice page and clear it out for us. But yeah, please get together with your neighbors. And so the idea is like first we add everything to the heap, everything that we want to. Everything to the heap. As many things as there are. That maybe have been a loop through a vector or something. But yeah, if the number of elements that you want to sort has a size n, so let's just maybe pretend that that was happening actually. Here, let me crop this. Just pretend that up above, that was adding all the stuff to the heap. All right, add everything to the heap in some way that you need to. And then you want to sort the stuff with heap sort. That's the process. So it's push, do a bunch of pushing, maybe an iteration through n things, create that vector, and do that loop. All right? So see if you can figure out what in the world is going to be the complexity of all this stuff. Any questions about that before I let you get started? So assume that pushing back to a vector is constant time. All right? Morally, it is. It's going to work out like that. But give that a try. All right? Remember your heap operations. What is their running time going to be each time you use them? So it's push is insert, right? Pop is remove. Pop is go look at the thing at the highest priority. How quick can we do that? Remember our running time. Pushback really is constant, but it's called amortized constant over the life of the vector. Oh, yeah, there was an email to respond. Give it another minute or so to think about it. So remember that the heap is always a balanced tree. Keep that in mind. If you're trying to remember your operation complexities. Almost caught it in time. All right, let's take a look and see what we're thinking. Do we have any ideas? Look at us. Logarithmic, linear. Ooh, one with a multiplication. Nice. Let's take a look and see what we're thinking. Let's see who is correct. But good job remembering that logarithms are involved here, right? Log is pushes running time as log, right? Logarithmic time. What else? We can scroll back up to those, right? Whee! So removal was log base 2 of n, or just log of n. And then insertion, pushing, in our case, that was also log of n, yeah? And so now the question is, I'm doing that a bunch of times, and so the one group who said n log n is correct, because you're going to do that n times, aren't you? So let's do this together. So okay, running time complexity. If you got n things that you want to push onto the priority queue, it is log of n time to push, and you're doing it n times, right? So it's log base 2 of n times n total, or just adding everything into the priority queue. Does that part make sense? I am sweeping some things under the rug, though, when I say that, because it's log base n, where n is the current size of the heap. And so you can do a better analysis here, but it still ends up being n log n. Because the very first time you add to your heap, you push back, there's just one thing. That's constant time, right? The second time, there was nothing there at all. The next time you push back, you've got one element. You maybe have to like swap some things, do a bubbling down, but like the size of the tree is relative to the logarithm of it always. So it's like the next push operation is big O of the size of the current heap. So it's big O of, log of the size of the current heap, which is 1. So it's big O log 1 for the second push. And now you got 2 things in it, so it's big O of log 2 for the third push. Does that make sense? Like it's always relative to the current size of the heap, because that's how big that tree is and how far down you need to maybe go. And then the next push is like, okay, it's big O of log of the number 3, log base 2 of the number 3, because that's how many elements are in there so far, to add the fourth thing, right? Because push is always log base 2 of the current size of the heap. All the way to big O for the very last push, you've got n minus 1 things in it, you're adding the nth thing, yeah? So the running time then is going to be relative to log base 2 of n minus 1, yeah? It just so happens, though, that you can bound this above by, like, n things, right? Like all of these. Turn them all into n's, or turn these all into log n's, right? That's an upper bound, right? For sure. Because log n is totally bigger than this. Log n is totally bigger than all of these. And you got n of those. So it's an upper bound for sure. You can also show that it's the tightest bound, but it takes more practice. It takes more knowledge. But that's why you can say that, and that happens to be the tightest bound. This is big theta of that. So it's good news, because that means your intuition works anyway, first of all. That's quite nice. So that's total for just the pushing part. That's just this stuff, right? That stuff right there. We now need to get to this stuff. What do we do now? So then you're looking at things and popping them off. Each time, then you're going to do, it's log base 2 of n, right, to do a single pop, and you're going to do n of those, yes? So again, it's n log n. But similarly, you could do a more accurate analysis where the first time you pop, it's always relative to the current size of the heap. So it's log of n for the first pop, right? Log of n time. And then now the heap for the next pop, it has n minus 1 things in it, doesn't it? So then it's log of n minus 1 for the next one, all the way down to, it's just kind of this backwards almost. So for similar reasons, an upper bound is still log of n times n. So you still get that. So it's this one to push, in total to push, and then this one in total to pop, and then to push to the vector, it's still constant time, so that doesn't add anything. And so that means it's this plus this, plus that, which is just 2 times n log n. You get rid of the 2, of course. So that means it's n log n to run heap sort, that is actually as good as you can do for a general purpose sorting algorithm. There are other sorting algorithms, which you have maybe read about already. You can't do better in general for arbitrary types. So n log n is the best you could possibly do. There are at that point it becomes the constant out in front of the n log n that tells you which one you should be using. It depends on your use case, of course, but this is, at least in terms of big O or big theta, a contender. You cannot do better asymptotically, which is awesome. Awesome to hear. You now know how to write a very fast sorting algorithm in that case. I hope you see that. That's pretty cool. All right. Are we ready to learn about how to mess with all the other pieces of the priority queues, template things, so that we can turn it into a min priority queue? Ready for that? It's going to look a little weird. Any questions about any of this first? We do have to trade time for space here for heap sort, don't we? Because you got to push it all into the heap. You can't just do it in place. Those are other trade-offs you maybe have to consider when you're trying to sort something. So do understand that there is going to be a space cost of what? I guess it's always going to be, there's going to be n, the size of your priority queue plus the size of your vector is always going to be n, isn't it? More or less, once you push everything to begin with. So it's going to be linear space. So that's kind of nice. But some sorting algorithms don't even need any extra space, so that's a trade-off. But yeah, let's learn how to change the max operation, because what if you wanted a min heap? So by default, like I was saying, it's disgusting, it was using the comparison class called less of t, which is doing the less than operation to prioritize bigger things, which just sounds very paradoxical, all right? So what less of t is, it is a comparison class. The way that it works is you can make a less of t object to compare two t values. You can make a less of int object, less, pretend t is something you care about, int or something. Here's how you make it. You make a comparison object of that class's type, compare, boop. You make an object, and then what is overloaded for that, because it's a comparison class, it's the parentheses operator. So it's as if you can call the object itself like a function on two things. And the job of a comparison class is going to return true for a less one, at least. It's going to return true when A is less than B. But the way that the priority queue type is going to use it is it's going to think of this from the perspective of the second argument, from the perspective of the B's rather than the A's. This is we're returning true when B has a higher priority than A. Okay, that's what's happening. Then A, I don't have enough there. Okay, and that means, okay, we're saying that because it's less than, right? We're saying that B has higher priority when, priority than A, when A is less than B, because that's what less is doing, all right? To spell it out, that's what's going on. So it's essentially using less than like greater than, because it's from the perspective of the second thing, okay? So that means, finally, if you want your priority queue to do not that, if you want it to do minimum, prioritize smaller things, then you need to give it a comparison class that returns true when the second argument is smaller. It wants to prioritize it when it's smaller. Give something back that give a comparison class that returns true when the second thing has higher priority, and we can define higher priority as smaller things. So that just means you give greater than, the greater than operation. You say, all right, use this operation, this symbol, to prioritize your B's over the A's. So when this is true, we're saying prioritize the B's where this is the case, which means that we're prioritizing smaller B elements. Smaller second argument things, all right? So that's still a lot of words and just a little vague. So here's when C++ has a heap, and it's you've given it an operation, you've given it a comparison function or class or whatever. You've got your object. All it's doing is C++ is I have my heap. I'm trying to either bubble up or down. I'm asking the question, should I put B above A? Here is how it's calling your comparison class. It's saying it's calling it with A first and B second, and then it's answering the question like this. If this gives back false, it's saying no, I should not put B above A. If it's saying true, this gives back true, it's saying yes, I should put B above A. That's all it means. Just think of it that way, all right? It's asking, should I put B above A? And so it's going to call it like this with B second. If it's false, it's saying, oh, okay, yes, it's already in the right spot. I won't bubble it up anymore. Or if it gives back yes, that's saying that B is higher priority than A. I need to maybe bubble it up the tree more, all right? So yeah, the moral of this story is you want something like, if you want a min heap, you give greater than. Like, all right, prioritize in this way, prioritize these Bs with this operation, that turns into a min heap. So it's always going to be asking, should I put B above A? It's going to ask this question. And if it gives back true, it says yes. So yes answers to this question prioritize smaller things. Okay? It's just disgustingly backwards, and I'm sorry. But that's how that works. Okay? But now I can show it to you. Let's make our own custom comparison class. You know that there's one called, you better believe that the existence of less implies the existence of greater. There's one in there already, but let's make our own just to get practice with this weird stuff already. All right, so let's go for they at. So I'll copy all of this stuff because we'll do a normal heap sort from smallest to biggest this way. If we get a min heap, let's do a min priority queue. Boop. So let's go like this. We'll say just like this. Let's make so all of this can stay the same. What changes is what I put here. So let's make a comparison class that prefers smaller second arguments. So it's essentially performing the greater than operation. All right. So let's make a greater than comparison class for our integers. Okay. That's what I'm going to do. I'm going to say this. I'm going to make a class that looks like this. A class, I'll call it greater than. Right? Greater than. And a comparison class, I'm going to be lazy and implement everything within the class right now. But a comparison class, it works by having an operator, parenthesis, parenthesis, like a function call operator, that returns a bool, true or false, whether or not, and then it takes two things. So you got parentheses after parentheses. It's like, all right, it takes two ints, int A and int B. And the job of greater than is to return whether A is greater than B. Yeah, that's all it does. And so that's what an object looks like. So think of it like, how would you use this? You'd make a greater than object, GT or something, and you say, you call this operator on it, the parentheses operator. Like cout GT on 42 and 43. Or let's do it backwards so that like you can see it be true. 43 and 42. Like that's how you call it. Like this is you hitting the parenthesis operator. So it's like you're calling your object as a function. Does that make sense? That's how it works. So very odd. Let me just show you that is a thing. Real quick. There we go, 1. So 1 for true, cool. So that's how it's going to be used by our priority queue. Cool. And so now when I want to do this, I want to use my priority queue with the greater than comparison class, you got to give it in order. So, okay, there are 3 template things as far as this type is concerned. It's got the T type, the thing that's in your priority queue. We got int there already. Then you give the container, by default it's vector, and then your comparison class, you give third. So if you want to get to the third thing, you have to go through the second thing. You have to provide that still as well. So we can just keep the default, but we have to explicitly say the default now. It's like, all right, how do I want you to store my heap? Please use vector of int, please. Just like that, all right? And then we can say, use the greater than comparison class as you're comparing your objects. For me, please. Make an object of that type, call it like this to prioritize the second argument whenever this gives back true, which is going to prioritize smaller things. Okay? That's how it's going to work. And with that in mind, I've done everything from before all over again. It's just like I've told it to prioritize things in this way now with this comparison. And we get increasing sorted order out of the deal. That's all we're trying to say here. All right. Any questions about that? Does that make enough sense? It's a little backwards. Again, it's like calling it in this way to prioritize the B's over the A's. When this is true, it's going to say B belongs higher up in my heap. So that's going to prioritize smaller things. If you give the greater than thing, you could have also said here the default was less of int, I guess. So you could have said, you could also just use greater of int, like that's baked into C++, just like less of int is. So a comparison class that just does the greater than operation. And then remember that the greater than, it looks backwards, the greater than comparison class, because it's involving the second thing, prioritizes smaller things. Backwards, but that's okay. We get it now. How would you make greater of t, greater of int, like a templated one of these? Let me show you. So instead of that one, let's essentially make what greater of t is, or less of t is. So go away, go away. So let's make greater than on t's real quick. So it's like template, class t, greater than on t's, or sorry, when we use it, we say that there, but we don't have to say it here. Class greater than, and then we're just going to take some t's instead. Ta, tb. Use the greater than operation on that, assuming it's implemented. The compiler will yell at you if it's not. So that's beautiful. So now I can't use this anymore. Oops. Where was I? Now we don't have this one anymore, but we have greater than on, I guess. This one now exists. Greater than on ints exists. And so you just say it like that now. Use the greater than on ints class, please. And now you have it working for any type that has a greater than operation. It is templated. You say, I want that one. Greater than on doubles will work just as well. Okay? That's a more generic one. Yeah, I think that's all that I want to say. Any questions about that? That is a comparison class. It's got this overloaded operator parenthesis. That's how you give things to the priority queue and tell it prioritize in that way, please. Okay. Let's see. Yeah, I think that's most of what I wanted to say. If we are good, I have an example that is pre-made that's really cool, but I need to potentially install things that I probably I have a new laptop from the school and I don't know if it's going to work properly. I have a really cool example that I'd like to show to you. Give me 1 second to try to make it work. I think it just takes too long to open this little window. And so what if we wait a little bit longer? That could be the answer. A very long program that I will never ask you to deal with. But let's say, let's have like a cn so that I can like get it ready into x, like cn into x. That could work for me. And then I need to compile it in this weird way. Oh, actually, it should be okay. We'll see. Let me actually undo that. I think it might be okay. All right. So I'm gonna compile this and I'm gonna show it to you. If it doesn't work, that's fine. I'll make it work and I'll show it to you next time. But I think it's gonna be happy. And then I have a picture of my cat Lonzo. Let me just try and make this work. Come on. Yeah, it does not look like it is happy. No. So sad. Why are you like that? Well, it seemed okay. At least it ran. Yeah, I might have to install some stuff, but I'll show it to you later. I'll work on it during your lab time, and maybe I'll show it to you then. But the idea was, it's a cool little example where you can pick your own maybe I'll show it to you next time. I won't explain it too much. But you can pick your own definition of priority. And so, just as an example, I made a cool example that worked on a virtual machine that might not work on this laptop anymore, where like you can turn your image, like you can take an image and you can prioritize pixels of an image. That's what I was about to show you. All right, because like what is an image but just a bunch of pixels, and the way that you store the colors of those things is different, and you can prioritize pixels by like taking their RGB values and being like, all right, I want the ones that are darker, I want the ones that are lighter, for example. And so maybe I'll show you that next time. I'll work on it myself, but if I can get it working while you're working on your lab, we'll see if I can do that. But yeah, here's something cool that I want to just along those same lines have you think about. So I don't know if I want to do this for you now, but think about this, all right? See if you can try it. I think we have time, actually. So see if you can try this. I'll have this code up. I'll show you this code that I have from last time. So using my min priority queue as a guide, I think this would be a great example for you. And I'll give you some hints if you need any. But try to take this code. Let me give it to you, actually. If you go to the code from class, you now have this file. And what I'd like you to do is try to make a priority queue of ints that uses this definition of prioritize. Let's say that B's have higher priorities than A's if B is closer to 42 than A is. Do you see how that produces a priority order that has nothing to do with maximum or minimum? Yeah. I guess it's how things are maximally close to 42, something like that. So, for example, if you added these numbers into your priority queue, prioritized by this, all right, prioritized by that, it should result in these values. Does that make sense? It should result in these values, 42, 41, because 42 is the first thing that's closest to 42. 41 is closest. The next closest thing. 45 is the next closest thing. 32 is the next closest thing. It's just like prioritize these numbers based on how far away from 42 they are. Like 42, of course, is right there. 41 is the next closest thing. Then 45 is over there. Do you kind of see how you might make a comparison class? Again, it's like you take two things. It's prioritizing the second thing when the second thing is closer to 42 than the first thing. Does that make any sense? Take a few minutes to try that. Like the other ones are like, what was the next one? 32 was way over here. Something like that. Then like 53 was over here, just the next smaller one. So try to go in that order. I think that's pretty cute and cool. All right, so try that. And maybe I can try to get that other example working while you're doing it. I want relib to work on. But yeah, take a second, open up the terminal, see if you can make that work. I've given you the code in minpriorityqueue.cpp in today's lecture folder. It's lecture 21. That is on our code from class page. So yeah, prioritize things that are closer to 42 while I take a minute to attempt to make that cool image example work. Whee! Why are you unhappy? And then we can try it together, maybe. Yeah, it just doesn't have colors properly. Prioritize things closer to 42. My hint is absolute value will come into play. It's a distance calculation, isn't it? And you want the smallest distance from 42, don't you? So give that a try. What if I tell this to wait? Um, no, wait, that's of course never gonna work. No, yeah, it's not. There's a bug in the way this is happening, isn't there? Alas. What if I get it working over here really quick? Yeah, I'll give you a couple minutes. I think, yeah, just the new version of the terminal I'm using is not happy with this library that I'm trying to use here, unfortunately. Hmm. There is a bug report about it. Hmm. Oh well.